Alright guys, let's discuss work and energy. So in physics, we define work as a product of force and displacement. So let's consider that with an example. So let's consider a body of mass m, okay, and that's acted on by a force F, okay. Let's say the force F causes the body to displace by S, okay, okay. So over here, we define W work as a product of F and S. Okay. Now over here, please note that F and S vectors are actually in the same direction and they are parallel. Okay. Now what if that were not the case, right? So let's consider another case where we have the same body, mass M. Let's say in this case, we have a chain attached to the body. We apply a force F, let's say in this direction, right, where the force F makes an angle theta with the horizontal and the displacement uh, is S in the horizontal direction. Okay, now in this case, work done W would be the product of the force component in the direction of the displacement, that would be F cos theta, right, dot S. Now this is of course the dot product of F vector and S vector, right? Because F is this and S is this and this is theta, right? So the dot product of these two vectors is the work W. Okay, so this is the definition of work in terms of a dot product of the force acting on a particle and the displacement S undergone by the particle because of the force. Okay, now let's consider a more generic case of, let's say, a particle that's moved, let's say, along this line. Let's say, let's consider time at which the particle is at this position P, and say the force acting on the particle is F in this direction, which is making an angle of theta with the displacement vector at that time, at that point P. Okay, so this would be the displacement vector ds. Okay, so in this case, the infinitesimal work done dW by the force F, which causes a displacement of ds, would be F dot ds. Okay, now if you want to find out the net work done, we would have to integrate that. So that would be W equal to integral of dW a to b is equal to F dot ds vector a to b. Okay, so this would be the generic definition of work, right? And of course, this is not easy to do, so therefore we would compute that in terms of x and y components of force and x and y components of ds, but we'll look into that a bit later. Okay guys, this quantity f dot ds integral is actually called as a line integral. Okay, this is the line integral of the force F along AB. Okay, now this is easy to see why this is called as a line integral, because we are doing an integral of F along the line AB. So therefore this thing is actually called as a line integral. Okay. Okay guys, so this line integral is not so easy to compute, right? So generally what we do is resolve the force F in x and y direction. So let's consider those directions. So we have x and y, and we say F is equal to fx I cap plus fy j cap. Okay, similarly ds vector is equal to dx I cap plus dy j cap. Okay, and then if when we consider the dot product of these two vectors, what we have is f dot ds is equal to fx dx plus fy dy. Okay, because of course when fx dot fxi dot dyj would be 0 because I and j are in uh, perpendicular to each other, right, 90 degrees. So this would be 0. Okay. So in for IIT JEE prep, of course, it's enough if you consider x and y direction. We generally consider plane motion, right? But the generic case would of course be f dot ds is equal to fx dx plus fi dy plus fz dz. Now it's important to know that. So this would be our general definition of work. Okay. So what this tells us is that this is actually work done in three different directions, right? X, Y, and Z. So that would be, you can sort of say work X, work Y, and work Z. Okay, it would be the network done. So let's say if we have a body which let's say undergoes displacement, let's say to this point. Okay, okay, and let's say the force that's acting on the body consists of Fx in this direction and Fy in this direction. Okay, and let's say the body has moved by a distance of x over here and by a distance of y over here. So in this case, work would be Fx x plus Fy y. That is the work done in the x direction plus the work done in the y direction. So it's also from this what also follows is that work is actually a scalar quantity. That's important to know. Work is a scalar quantity. Also, it's important to know that work is actually dependent on the reference frame. Why? Because work is the product of F and S. Now F is independent of the reference frame. Okay, independent of a reference frame. S, of course, displacement is dependent on reference frame. Therefore, work is dependent on reference frame. Okay, so let's consider that with an example. So let's say if we have a person, let's say inside of a lift, okay, and say that lift is going down, let's say in this direction, there's displacement S, okay. So in this case, the work done by the force of gravity would be mg, that would be the force on the person, multiplied by x, the displacement in the vertical direction, that would be mgx. Okay, now this is important to note that this work done is in the reference frame of earth. Okay, but if we consider another reference frame, that is of the lift itself, so if we have a reference frame that's let's say attached to this attached to the lift itself, in this reference frame, the work done by the force gravity would be g times 0, because with respect to the lift itself, the person is stationary, right? So therefore, the displacement is 0, and therefore the work done by the force of gravity on the person is 0. So therefore, it's important to note that work is dependent on reference frame. Alright guys, so another thing that's important to note is that we always speak of work in terms of the particular force, right? So for example, if we have this body of mass m, and let's say this body of mass m is acted on by a force F, and let's say that the surface has some friction. So in that case, we would also have a friction force over here, right? Also, there would be another normal force in this direction, and you would of course have W, that would be the weight itself. Okay, so in this case, so the work done by the normal force W, and let's call that, would be N dot S. So let's say the body has undergone displacement of S in this direction. So that would be N dot S dot cos 90, right? Because N is in this direction and S is in this direction. That would be 0. Similarly, the work done by gravity would also be 0 because mg is in this direction and S is in this direction. The dot product of these two vectors would be 0. Then the work done by this F force would of course be F dot S, and the work done finally by the friction force would be Fr dot S dot cos 180 because Fr is acting in this direction and S is in this direction. They are making an angle of 180 degree with each other. They would be Fr dot S minus, that would be work done by friction would be negative. So of course we do have a concept of negative work. Uh, so whenever the force and the displacement are in separate directions, they're not aligned, we have the concept of negative work. Okay. Okay, so in this particular case, what would be the net work done? Let's consider that. So we can say W net is the sum of the individual works, that would be Wn, that's work done by the normal force, plus W gravity, work done by the gravitational force, plus work done by the F force, plus work done by the friction force. Okay, of course that would be 0 plus 0 plus F dot S plus minus of Fr dot S. Okay, of course that would work out to F minus Fr dot S. Now what is that quantity? So that is actually a dot product of F net and S. Okay, because of course if you consider the free body diagram of this particle, you have mg in this direction, you have the normal force, you have the F force in this direction, you have the friction force in this direction. Of course, we assume the body has acceleration in this direction. So we have n minus mg is equal to 0 because the acceleration in the vertical direction is 0, and we have F minus Fr is equal to ma. So of course the net force therefore is quite simply F minus Fr, right? Therefore the work then becomes F net dot S. So in this case, we could say that F net is this, right? And this is S. These are both vectors. And F net vector dot S vector is simply F net dot S because the vectors have 0 angle between them. Okay, so let's again consider the general case. So we have the particle move along a general line AB, right? So let's say at this point P, the particle moves ds. And let's blow that up. This is ds, right? And this is ds, and let's then resolve that into x and y direction. So we have x and y. So this would be dy and dx, right? So then the force acting at this point is, let's say, F, which is Fy in the upwards direction and Fx in the x direction. dw for the displacement ds would be Fx dx plus Fy dy. It would, just be a scalar sum of the work done in the x and the y direction, right? So therefore, again, you would integrate that and you would get Fx dx plus Fy dy integral from a to b, right? In other words, it's the scale up sum of work in different orthogonal directions. In different orthogonal directions. Okay. Okay, now let's consider an example. So let's consider a body of mass m moving with velocity, initial velocity v naught, and let's calculate the work done by the friction force to bring this particle to rest. Okay, so in this case, we would have from Newton's second law, the free body diagram of the particle would say, so it's Fr in this direction, we would have mg in this direction, because you would have normal force in this direction. And of course, n minus mg is equal to 0, that would be the y direction, right? And in the x direction, you would have minus Fr is equal to ma. This would be the x direction. Okay, now we have minus Fr is equal to ma. Now we know from kinematics of particle that v dv is equal to a dx, right? So we can say a is equal to v dv by dx, right? So we have minus Fr is equal to m v dv by dx. So we have Fr dot dx is equal to mv dv, right? So we note, of course, that this quantity is Tw, right? So we have Tw is equal to mv dv. So we have Tw is equal to mv dv, and we integrate that from v naught to 0, right? And we have therefore half mv square v naught to 0 is equal to half mv naught square, right? So as you can again see that the friction force is in this direction, which is opposite to the displacement. Therefore, the work done has a negative sign. It's a negative quantity. All right, now let's look at some examples of the work of a force. Let's first consider work of gravity. Let's consider this path traveled by a body of mass m. So at various stages, the body is in these positions, which are defined from point A to point B. Okay, this is the surface of Earth. Now, let's now define our x and y direction. So we have x, and we have y, and we have point A at elevation of, let's say, YA, and we have point B at elevation of YB. Okay, now the question is, what is the work of gravity if a body of mass m moves from point A to point B? Now that would be integral of f dot ds vector from A to B, right? And you could then write the force of gravity as mg minus j vector dot that with the dx I cap plus dy j cap. Okay, integral from A to B. So this of course works out to minus mg dy integral of A to B, and we can now take out mg outside of the integral. We simply have dy A to B, which then works out to minus mg yb minus ya. Work done by gravity is mg ya minus mg yb. Okay, so now let's look at another example. Let's now look at the work of a spring force. So we have a spring which is initially not stretched, to which is attached a body of mass m. Then after some time that spring is stretched. Let's actually define x equal to 0, that is the origin, at the position of the undeformed spring. Okay, and let's say that this is position B over here, or x is equal to, let's say, xp. Now we know of course that the force of the spring when we stretch the spring is in this direction, and that's kx, right? And of course when we have a spring which we then compress, right, then we have a force acting in this direction. So the force of course always acts towards the mean position. Now the work done by the spring force would be integral of A to B f vector dot ds vector. Now that would be kx, and then we would say minus I cap I and dx I cap plus dy j cap. Okay, integral A to B, and that would work out to minus kx dx, and you would integrate that from the point A to B. And of course that is kx square by 2 from 0 to xp. So that would be minus k xp square by 2. That would be the work of the spring force. Okay, so now you must have noticed one thing, right? That when we consider the work of a gravity, then the work is only dependent on the initial and final positions, right? So we have work of gravity is mg ya minus mg yb. Similarly, for the case of the spring, we have, so in this case, the work of the spring force is half kxa square minus half k xp square. Now, in both cases, you have the work dependent only on the initial and final positions, right? So whenever that happens, we call that force as a conservative force, where the work done by a force is only dependent on the initial and final position, we call that force as a conservative force. So what we can do now is that instead of carrying out the line integral, so instead of doing this, if work is equal to integral of a to b f vector dot ds vector, we can, for the case of the conservative force, define a function. So let's see how that works. So we have position A and position B, and we can say that, let's say we define u as a function in y, and at this point A we have u take the value of mgya, and at the point B we have u take the value of mgyp, and in this case we can define the work done as simply the negative of the change in this function, right? So we have negative of mgyb minus mgya. Okay, so this function, right, so u is equal to mgy, we call this as the potential energy function. Okay, this is the potential energy function. Okay, okay, so now let's look at the value of this potential energy function. So now let's say if we have this kind of an incline, let's say if we have a body of mass m which climbs this incline, and we define this as y is equal to 0. So we have the height reached as y is equal to h. Okay, now we know that the potential energy function u is defined as mgy. Okay, that means at this point A we have ua is equal to mgy with y being 0, this is 0. Similarly, at this point C, we have uc is equal to 0. And at the point B, we have ub is equal to mgh. Okay. Now, if you want to know the work of the force of gravity from point A to B, we simply take the negative of the potential energy function from the points A to B. So that would be negative of mgh minus 0. That works out to minus mgh. Okay. Similarly, if you want to calculate the work of gravity from the points P to C, we have again the negative of delta U. That would be minus of 0 minus mgh is equal to mgh. Okay. Okay, now from the potential energy function relationship, right, between work and delta U, it's very clear that if this quantity delta U is negative, then work done is positive, right? So what that means is that if U reduces in value, work done is positive, right? So what that means is that potential energy is the ability to do work. And that is qualitatively seen in this case as we traverse from the point B to the point C. The potential energy decreases from mgh to 0 and work is done by the gravity force. Okay, so now let's discuss the work energy theorem. For that, let's consider the general case of the particle move from point A to point B in any fashion. And let's say at point B, it's acted on by a force F in this direction. So we have Fx. In the x direction, we have Fy in the y direction. Now we know from Newton's second law that F vector is equal to ma vector. Now we can write that into x in x and y direction. So we have fx is equal to max, and of course we drop the vector. We have similarly fy is equal to may. Now we know from kinematics that a dx is equal to v dv, right? Therefore, a is equal to v dv by dx, right? So we can then say we have fx is equal to m v dv by dx, because this is vx. Similarly, we have fy is equal to m vy dvy by dy, right? So then what we can write is fx dx is equal to m vx dvx, and fy dy is equal to m vy dvy. Now we know, of course, that these quantities are simply the work in the x and y direction. So this is actually dwx and this is dwy, right? So net work we can say is dwx plus dwy, because work being a scalar quantity, we can simply add them up. So that would be mvx dvx plus mvy dvy. Now to get the net work, we would have to integrate that from a to b. So we have dw integrate from a to b equal to mvx dvx a to b plus mvy dvy a to b. Now of course vbx square plus vby square is simply vb square, right? So the velocity at point P is a vx and vy, and this is vb, right? So similarly for va square as well. So what we have finally is m by 2 vb square minus 1 by 2 mva square. That's the net work done from A to B. Okay, so now this quantity half mv square is actually called as the kinetic energy of the body. So what the work energy theorem then finally says is that the work done, the net work done on any body is the difference in the kinetic energy of the body. That is the work energy theorem. Now you would note that we have derived this for the general case. Therefore, this is always true in the case of a particle or a mass, and this is true but only in the case of a Newtonian frame of reference. That's important to note. So that's true in the Newtonian frame of reference. Okay, now finally what we can conclude over here is that since W net is equal to delta KE, now W net itself actually can comprise of work of different forces, and generally we differentiate between the work of a conservative force and the work of a non-conservative force. So therefore what we can write is work of a conservative force plus the work of a non-conservative force equal to delta KE, right? Of course, we know that the work of a conservative force is equal to change in the potential energy function. So if we substitute that into the equation, what we have is minus delta U plus work of the non-conservative force is equal to delta Ke. Therefore, what we have is work of the non-conservative force equal to delta Ke plus delta U, right? So this is another form of the work energy theorem. Okay, so now let's continue to build on that, right? So what we can write is WNC is equal to Ke final minus Ke initial plus U final minus U initial. And we can rearrange the terms to say Ke final plus U final minus Ke initial plus U initial. Now this quantity together is called as the mechanical energy. What you can write is we have E final minus E initial, work of the non-conservative force. This is another form of the work energy theorem. It's important to note that E, which is the mechanical energy, comprises of potential and kinetic energy of the system. Okay, so now let's look at an example, right? When we consider a ball at height h, right? Initially, of course, the ball is at rest at this height, the v is 0, and then the ball is dropped and it falls all the way down. And let's define this as point A, this is point B, and the ball again rises up after bouncing to attain the same position C. Of course, A and C are the same position, but we show them side by side so that we can see them separately in the figure. Now, let's apply the work energy theorem in this case. So, at the point A, we have energy point A is equal to half mv square, right, plus mgh. Of course, at this point v is equal to 0, so therefore this works out to mgh. Similarly, at point B, we have half mv square at point v is equal to vb at this point, plus mgy, where y is 0. And of course, vp is quite simply 2gh under root, right? From kinematics of particle, when the ball is dropped from a height h, initially the velocity is 0, then it attains a velocity of under root 2gh, right? So therefore, we have Ev is equal to half m2gh plus 0. So we have mgh. Okay. Now at point C, we have EC is similarly equal to half mv square. Of course, when it rises up, it again attains the velocity va plus mgy, y is equal to h. Of course, when it rises up, va is equal to 0. EC is equal to 0 plus mgh. That works out to mgh. So as you can see that EA is equal to EB is equal to EC is equal to mgh. So when we look at the third form of the work energy theorem, so what this tells us is that there's no non-conservative force acting on it. So the third form says WNC, work of the non-conservative force, is equal to delta E, right? Now, since EP minus EA is equal to 0, this implies that the work, the non-conservative force is 0. Of course, we can see clearly in this setup that the force acting on the particle at any given point in time is quite simply mg, except at the point B, right? At the point B, we have a normal force acting in this direction. However, it does zero work because as soon as the ball leaves the ground up, there is no force acting, right? So the force, the normal force itself does not cause that motion, right? So the displacement is zero, therefore the force is normal and the work of the normal force is zero. So therefore, during the whole travel from point A to B to C, the only work that's acting on the body is the gravity force, which is a conservative force, and therefore we have the work of the non-conservative force is zero because there is no non-conservative force in this whole scenario.